Hi there. The vector equation of a line. Now, points on a line, each will have a position vector. And that position vector is relative to the origin. Yes? So, relative to the origin. Later on, I'll actually sketch a diagram so you will actually see this. But these are the things we need to be aware of as we develop a vector equation of a line. We need to describe the position vector of any point on the line. So this is what we need to be able to achieve at the end of this video, to be able to describe the position vector. And remember, the position vector is relative to the origin of any point on the line. And then we need to define the complete set of points on that line. Right, so these are the key things. We know that I've forgotten the word point here. Each point has a position vector. And remember, a position vector is a vector that is rooted at the origin and describes the point. So it's a point connected to the origin. We need to describe the position vector of any point on the line and define the complete set of points on that line. Now, if we consider a line in the xy plane, and this is the line we're actually considering in the xy plane, whose direction vector is d, as shown here, and it passes through a point A with position vector A, then if P is any point on the line, then we have AP is parallel to D. It's in the same direction, though they have different magnitudes. It's in the same direction, that makes it parallel. This implies that A to P is a scalar times the direction vector D. So there are different magnitudes, so in order to get from A to P, you must multiply your direction vector D by a scalar quantity lambda. Also, O to P, or origin to P, equal to O to A, together with A to P. Yeah. So O to A together with A to P is from O to P is equal to O to P. Now this implies that I forgot to add this. Our position vector of the point P is R. So this now implies that R is equal to A added to lambda times D. Now what are the key points about the vector equation of a line here? Each value of lambda, so each value of lambda, whether it be positive or negative, gives the position vector of one point. So it gives position vector of 1 point. So it's a way of modeling the movement of R along this line here. All we have to do is change the value of lambda and we get a different position. And for different values, we can actually find a position vector for each point on this line. So we know now that this is the vector equation of the line. Just this specified line here. It's in the XY plane. And we've specified that these 2 points A and P, with position vectors A and R, respectively, with direction vector D. Now here are some examples. Suppose we have the vector I minus 4j, which passes through, so it passes through the point minus 5, 7. We can find that R is equal to minus 5 I add 7 J added to lambda I minus 4j. So this is for the vector I minus 4j and passing through the point minus 5, 7, so it's some point in XY plane. This is the vector equation. So for different values of lambda, whether they be negative or positive, will give you different points on the line specified. Here's the next example. Is we have a line with direction vector minus j, add k, three-dimensional, and it passes through five, 1, 3. So the point 5, 1, 3. And this has a vector equation R 5i add j add 3k add lambda times the direction vector. So a line with direction vector I minus j add k and passing through the point 5, 1, 3 has a vector equation of r equal to 5i add j add 3k add lambda times I minus j add k. Thanks for watching. I'm Alistair.